video.
Okay, can you hear me? Is this microphone? Okay. So yeah, so I'm going to tell you about basically this mathematical animation software called Manim. And I have two goals. The first goal is to convince you that like it's worth considering to even try to make a mathematical animation for any reason. And the second is to convince you that it's also not very hard. So for the first goal, I just have made a little lesson that is going to be sort of aided by some animations. And this is all made in Manim. So yeah, I guess I'll just get into the lesson. So, oh, sure. Okay, you'll do it. Okay. Okay, so here's the question for you. Have you ever dropped a ruler into your glass of water, or been wondering why a polar bear has half of its, or it has its head separated from its body? Okay, maybe you know why. It's the principle of refraction, which basically is telling you that when light moves from one medium to another, and there's sort of two different speeds of light in, say, in air and water, then the light will do some weird bending thing. And it's not just a weird physics fact as well. It has very practical applications, such as if you are spear fishing and you see a fish in the water, and you shouldn't just throw your spear to where you think the fish is, because of refraction. The fish is actually going to be in some other slightly different position. So if you know the law of refraction, you can like calculate where exactly the fish will be, and then you can catch the fish properly. So anyway, let's set this up mathematically. So suppose we've got some water and maybe 2 points, one above in the air and one in the water. And when you see the fish, or when you see the fish, basically that's I guess a beam of light or something traveling from the fish to you, or maybe from you to the fish. Maybe you're shooting some like vision rays out to hit the fish. Either way, it's sort of mathematically equivalent, but let's just say there's some light traveling from one point to the other, and you see it's bending. But why should it bend this way and not like any of these other different ways to get from that point to the other point? So to answer this question, we will turn to this thing called Fermat's principle, which is that light travels along the path which takes the least time. Okay, so pretty clearly, if we're not really changing between the air and the water, if we're just traveling through the air, well, we should go in a straight line, and same thing if we're just going in the water. So really the only parameter that we have here is this thing x, which is what I'm going to call the distance sort of along the water's surface, I guess, between the point in the air and the intersection point between the light ray and the surface of the water. And as we vary this, we can sort of plot the time that a path will take. So let's see what that looks like. We'll get a plot like this, and notice there's going to be some sort of minimum value there. And if you think about it, I have drawn this picture so that, and this is maybe makes sense, so that the speed of light in water is slower than in air. So maybe that should give you some intuition as for why it should be bending, I don't know, this way instead of that way. Anyway, to really actually calculate where exactly this minimum will be, we can add a few more numbers or letters, I guess. So HA is going to be the height in the air above the water surface that the point in the air is. HW is going to be the height below the surface that the point in the water is, W for water. And then D is going to be the total distance between the 2 points, okay? And we can now write out what the time will be in terms of all these letters. Oh, actually, sorry, we need one more thing. We need the velocities of the light in air and water. So we have VA is the velocity of light in air, VW is the velocity of light in water. So then we can write that the time is equal to this big expression. And those square roots are basically just the distances along these two segments. That's just using Pythagorean theorem. And then if you have distance divided by velocity, that should give you time. So there's two things here. Each one corresponds to one of these two segments. And we can differentiate this with respect to time because, well, we're trying to find a minimum. So that's what we're doing. We're going to use some calculus. And I'm not going to explain why this derivative is the way it is, but you can just look at it and convince yourself that it is correct. Good job. And now basically, since we're trying to find a critical point, we want to find a place where this derivative is 0. So really these two fractions should be equal to each other. But now notice the, let's just think about what some of these quantities are. So this x that I've colored in red is equal to this red line that I've drawn, the length of that red line. And similarly, the d minus x, which I've now colored in blue, is equal to this blue line under the water. And now these square root symbols, the square root of x squared plus HA squared is this hypotenuse, as we had it earlier. And I've drawn that in orange. And similarly, the other square root is going to be this green segment. So I guess this is sort of begging for us to put in some sort of extra line to make some triangles. So that's what we'll do. There's a triangle. And if we have triangles, we like to know their angles, or at least one of them. So theta A is going to be the angle between this normal and the ray of light that is above the water in the air. And then theta W is going to be the same angle, but for the ray that's in the water. And you'll notice that the red over the orange is just the sign of theta A. And similarly, the blue over the green is the sign of theta W. And so what this really reduces to is that the sign of theta A over VA should equal the sign of theta W over VW, or if you like, the ratio of the signs equals the ratio of the velocities. So we can clean this up a little bit, and that's all really the information that we need, just the velocities and these angles. And we've proven something that is known as Snell's law for refraction. So are there any questions about that before we move on? Okay, if you don't have a question for me, then I have a question for you. Why is Fermat's principle true? Okay, if you don't have an answer for me, I have an answer for you. What? Okay, tell me then. Okay. Sorry, I'll tell you the answer, or at least I'll try to give you some intuition for why Fermat's principle should be true. So in order to do that, we need to talk about the wave theory of light. So to make things simple, let's just suppose we have a homogeneous medium. We're not doing anything that like a light is going between air and water or vice versa. And the wave theory of light says that light propagates from a light source in waves, basically. And so let's say we have a light source here, then it'll start producing waves of light once you, I guess, turn it on. And that'll look something like this. By the way, I hope nobody will like get a migraine from this. I don't think that anyone will, but if you're prone to this, like close your eyes, I guess. Okay, anyway, light will propagate in a wave from a source, but that's not the only thing that the wave theory of light tells us. You also basically need, anytime this wave touches some part of the medium, that point also becomes a new point source for the light at the amplitude that it touches the wave at. So for simplicity, I'm only going to show you two more points here on this boundary when basically they'll start emitting light once the light touches them, if that makes sense. So hopefully this animation will clear that up. So also all of these sort of point sources will emit waves that will all interfere with each other and make some sort of interference pattern like this. Of course, that's not all. We should be doing this at every time as well. We should be doing this like, constantly adding more point sources at every point that the wave has ever touched. So to approximate that, I'm only doing two more, just because it would have been a bit more complicated. Anyway, the point is, you'll see light in this picture where there's high contrast. So that means that there is like a wave or a bunch of waves that are sort of interfering with each other constructively rather than destructively. So like in this picture, like let's say white is negative and black is positive or something, and gray is 0. So where you see the highest contrast is where you'll actually see the waves, and that's where you'll see the light. But like I said, we should have been doing all of this like at every point in time and every step in time and every point in space that it's been touched, and that's a bit complicated. So instead of like thinking about it like this, we're going to use a different but equivalent formulation of the wave theory of light, which is basically that light will take every path, and it will also do this oscillatory thing along the paths that it takes, and these paths will sort of interfere with each other, okay? So let's go back to Fermat's principle. So let's suppose we have 2 points in this medium, and here's a path which is not a path of least time. So light will take this path, like I just said, but it will also take this path, which is nearby, and it'll take all of these other paths that are sort of very close to this other path. And I want you to notice that, like, as this thing moves from the bottom to the top, the time that this path will take sort of increases, the darker orange path. So if you think of this as, I don't know, you have some function that takes in a path and gives you the time that light takes to traverse that path, then the derivative of that function, or that functional or something, will be positive for this yellow path, if that makes sense. If you're considering it along this variation of these darker yellow curves, okay? Okay, but there's another part of the wave theory of light, which is that light will sort of alter, or it'll sort of oscillate along the path. So let's draw that in. I'm now representing that with red and blue. So let's suppose that the light is starting from the left dot and going towards the right dot, and basically it'll start, I guess, red very close to the left dot, and then it'll start oscillating as it travels along the path. And notice what happens at the other endpoint as you change this path. It sort of has some sort of positive drift as the paths change. And so if you think about all of these paths that are all nearby to this yellow path, they'll all sort of be out of phase with each other, or they'll be, you know, shifted by something which corresponds to that derivative of the time functional that I mentioned earlier. So the point of all of this is that since all of these paths are out of sync with each other, or they're sort of like shifted in a way that will cause them to all interfere destructively, you won't actually see light travel along this curved arc, okay? And I'm also like massively exaggerating the wavelength of light. So really it should be much smaller than what I'm showing on the screen here. So you will, like, in the video, it looked like it was sort of still synchronized over at the left side, but it really will start to go out of sync very quickly. So you won't see any of this in traveled by light. But let's, for contrast, see a path that does take the least time, such as this straight line. And again, there's a bunch of paths that are nearby, but this time for that time functional, whatever it is, since this is a path of least time, this will be a critical point. So meaning that, like, if you consider the time functional on this variation, the derivative will be 0 at this straight line, okay? So if we draw in those, you know, the oscillations again, then as we move it up and down, we can notice it still does change a little bit over here, but now it's only a second order change. So the point is that, like, the paths that are really close in space to this straight line are also really close in time. So they'll sort of all be synchronized up with each other, and they will interfere constructively, and then you will see some light traveling along this straight line path. So this property that I mentioned a few times without really defining it, of having the derivative of the time functional be 0, is called stationarity. And so this bottom path is stationary, and you won't be surprised that this top path is non-stationary. So really what I've hopefully intuitively helped you understand is that light travels along stationary paths. And just for comparison, we can see them both at the same time, I guess. So yeah, this one's way more out of sync than that one. But now maybe you have a question, or at least I have a question for you. So we've shown that, or hopefully you understand that light travels along stationary paths, but are there any examples where the previous version of Fermat's principle, that light travels along shortest time paths, is false? Like, are there any stationary paths that are not shortest time paths? Well, anyone, you have an answer? Yeah, there's longest paths that you have to sort of look kind of hard to find something like this, because in a homogeneous medium, if you're just everything is Euclidean, you won't really find any stationary paths that aren't shortest paths. But if you look at some more complicated situation, like this picture that I've got, then you will find stationary paths which are not of least time. And maybe this is unclear what this is, but this is a convex, or I should say, no, it's a concave mirror. So it's sort of like a spherical mirror, and you're on the inside. And if you think about it, and I'm going to leave this as an exercise for you to think about, if you think about a reflection on the inside of a spherical mirror, this will be a stationary path. You'll find a stationary path, but that stationary path will be one that takes the most time, not the least time. Okay, and that's all that I had for this lesson. So are there any questions about the lesson? And how much time did that take? About 15 minutes, okay. Okay, if there are no questions, we can just move on to my next goal of the talk, which is to sort of try to explain to you how to do some of the things that I did in that video. So like I said, I'm using this program called Manim, and Manim is actually just a Python library, basically. So how many of you have used Python before? Okay, a lot of people. How many know what like classes and objects and stuff are in Python or in any other programming language? Okay. Okay, cool. So you don't need to know any of this stuff in order to understand the rest of this. I think it'll be pretty transparent, or hopefully pretty transparent. But if you do understand it, then I'm going to say some things which might make more sense to you. Okay, so like I said, Manim is a Python library. So I'm not going to tell you how to install it. There's like a bunch of documentation you can find online for how to install Manim, or if you have done Python libraries before, you can just like install it however you would normally do that. But anyway, the first thing we're going to do is this, import everything, obviously. And now let's try to make a quick animation. So every animation, when you're starting off, we'll start something like this. We are defining a class, which is a type of scene, and I'm calling it A1 in this case. And the thing that you need to do to make a scene do something is to define its construct method, okay? So in the construct method, we'll write everything that we're gonna do for the animation. And for example, let's say C is a circle, and we'll say self.add C. And now, once we've written this code, we can go into another terminal, and this is now I'm in the place where I've stored this file, which is called animations.py, and we'll type, is that big enough? Maybe I'll make it a little bit bigger. So the basic thing that you would type is manim, and then you pass in the file, animations.py, and then you pass in the specific scene that you want to render. So that's A1 in this case. But I'm going to actually do a few more things, and I'll tell you what they are. So if you pass this -p to it, that means that Manim will play the file after it's rendered instead of just sort of saving it to somewhere on your computer. And then here's another one that you don't normally need to worry about, but this is just telling it to only tell me if there's an error, so it doesn't fill up the screen with a bunch of stuff. So there you go. There's our scene with a circle. And okay, maybe that's a little underwhelming and there's not really any animation going on. I've just added a circle. But let's see if we can change that a little bit. So let's do that, and let's see what that looks like. Oh no, it's in my, there we go. Oops, it already played. There we go, it made the circle, it created it. So let's go back and maybe talk about exactly what's going on here. So circle is a type of object in Manim that is one of the basic things in Manim, and it's called a mobject, which sounds weird, but it means mathematical object. So it's basically any of the things that you can involve in your animations. And now another thing that's going on here is this this create C thing. that's an animation. So create will take in some object, and then it'll return an animation that's like showing the creation of that object. And then you have to pass animations to this method called self.play. So that's how you make an animation go, okay? And then I've also done this thing, self.wait, which basically says, instead of just ending the video right there, wait for 1 second so we can see the circle being created, or having been created, I guess. So let's see some other things that we can do in Manim. So maybe S is a square, and maybe we want instead, okay, so let's create C, and now let's do transform. We'll turn the circle into a square, okay, and then we'll wait. So let's see what that looks like. Okay, we create the circle, and it transforms into a square. Yeah, I know, very, very exciting. What else can we do? So there's a bunch of built-in animations and objects and stuff for you to play around with in Manim, and maybe I'll just show you a few more of the things that you can do so you can get a feel for exactly how easy it is to do this. So let's say maybe instead of transforming the circle into a square, I want to put the square next to the circle. So then I can just say S dot next to C. So that means S is going to go next. The square is going to go next to C, the circle. And instead of doing this, I'm going to say just create square. And this hopefully will be pretty predictable what it's doing. It's going to create the circle and then the square next to it. So there's a lot of like weird, you can just, there's a lot of built-in things that'll sort of do something that you might not think is completely trivial to like code up, but it'll sort of just do it automatically for you, which is pretty nice. Okay, let's see what else we can do. Let's get rid of the square. We don't need it right now. And let's say that C should move to 2 times right. Okay, that maybe looks a little weird, but Manim has its own sort of like coordinate system, and basically the vector that there's this thing called the origin, which is the center of the screen. Then there's right, which goes to the right, left, which goes to the left. There's up, and then there's down. And the top of the screen is 4 times up, and the bottom of the screen is 4 times down. And then like the left and right, since it's not exact, it's like 7.1 or something. So let's see what happens when we do this. So we've created the circle, and then the circle moves to 2 times right, but that didn't look very smooth. It sort of just automatically jumped over there. But a cool thing that you can do, so notice this C.move2 is something that I'm telling C to do. It's a method of circle, okay? So if instead I say C.animate.move2, it's not gonna work quite yet because C.animate.move2 now, if you sort of put this word animate in between C and the method, it will return an animation, but that means that I need to do self.play because it's an animation now. So let's see what this does now. Wow, there you go. Okay, let's see what else I can do. Oh yeah, so another thing that you probably would want to do with Manim is like use LaTeX. So you have to have LaTeX installed on your computer as well. Like you can't, Manim doesn't come with LaTeX, but if you have LaTeX installed on your computer, then this will all work fine. Which I know is not a trivial thing to say, but I think you can do it. Let's call this one A2. So the LaTeX is going to be another mobject, and there's actually multiple ones. You could use something called tech, or it could be math tech. And a nice thing to do here is to use these R strings, which is a feature of Python, which basically means you don't have to like escape the backslash. if that didn't make any sense to you, then don't worry about it. You can just basically type raw LaTeX here. And you don't have to have commas in between things, which is a little weird to me, but that's the way it is. What is this, pi squared over 6? Okay, so we've got our math tech object, and we can say self.play create tech, and then self.wait. So create is something that you can basically pass in any, oops, that's the wrong one. We want A2. Create is a thing that will take in basically any object and make a creation animation for it. Now, it didn't look very great, I gotta say. So there's a few other things you can do instead of create. So for like to bring something onto the screen, you can also do like fade in. So let's see what that does. It fades it in. Unsurprising. You can also pass some weird arguments to fade in, like shift equals up. And let's see what that does. It faded it in, but it shifted it up. So there you go. But if you're doing stuff with like LaTeX or just text in general, you can also use this method, which is kind of nice, called write. So let's see what that looks like. And that's sort of like create, but like it looks a little smoother, I guess. Okay, so you've got your LaTeX, but you don't want to just like show it on the screen. You want it to sort of be interactive or move around or animated or something. So let's see what we can do here. I'm gonna make a new one. Okay, so let's say we have an equation like this. We have a squared plus b squared equals c squared. Okay, if we want to make things move around okay, let me just tell you what we're going to try to do first. So instead of a squared plus b squared equals c squared, maybe we want a squared equals c squared minus b squared, right? And let's say, let's write T1, let's wait, let's transform, oops, T1 to T2, and let's wait, and I guess that's it. Let's see what that does. Oops, I did it again. Should be A3. Okay, this is taking a little bit of time, so I'm going to tell you about one other flag that you can do. It also looks kind of bad, so let me tell you about two things at once. Actually, okay, let me tell you about this flag first. So here, let me just clear this so you can see. So if you type the command flag Q, this is going to tell Manim which quality to render in. So if you're going to like, use this for your final project, maybe you should render in high quality, but for now, I'm just going to like render it in medium quality, and hopefully it'll be a bit quicker. Yeah, it's a bit quicker. You can't tell the difference. It still doesn't look great there. Anyway, let's go back here. So instead of just transforming T1 to T2, because that sort of just like does the most basic thing, we're going to get a little bit smarter about this. And we're going to isolate each part of this LaTeX expression by putting double curly braces around it. This is a like Manim specific syntax that is, wait, let me see if I can do, oh no. This is Manim specific syntax that basically will tell Manim that these pieces of the LaTeX should be sort of thought of as separate things that can be moved around. And then instead of saying transform, we're going to say this thing called transform matching tech. Okay. And now let's see what that does. Oh yeah, I still want medium quality. What's it doing? There we go. Okay, there we go. And that looked a lot nicer, right? Let's see it again. Yeah, so I don't know, hopefully you're hooked already, but that definitely got me. Anyway, let's see what else we can do when we've isolated these like pieces of the these pieces of the LaTeX. So we can say so we're gonna actually change the color, but like just of A squared, and we're gonna make it red. Yeah, question. Let's see what happens. Let's see what happens. So which bracket do you want me to put the plus into? Oh, like by itself. Yeah, let's see. I see what you mean. Yeah, it will actually just do the same thing as before, I think. Let's see what happens. But because the plus doesn't match anything in the mind. Oh, maybe you have some other issues actually. Okay, well, there you go. Yeah, there are some bugs with this. And I should say that this is like an open source project right now. So there are bugs for one, but for two, there is a Discord server that you can join if you experience any bugs or if you're confused about some sort of like feature or behavior of Manim. You can join this Discord server and you can just like talk to the person who wrote the code. And so it's pretty convenient. And like, if you see this, you can tell them about the bug. Actually, I already told them about this bug and they haven't fixed it yet. So anyway, yeah, there you go. Things can go wrong, especially with this LaTeX stuff. But I think that is more LaTeX fault than Manim's fault, but I'm not really sure. Okay, let's undo that. And instead, we're going to set the color of A2 just to red. And again, I'm saying t2.animate.set color by text, so it's gonna like fade in the red or something. Okay, let's see. So we did this, did that, and now A squared is red, I should say. Yeah, so those are a few of the things you can do with LaTeX. Yeah, question. Yes, you can, and I don't remember the exact syntax of this, but let me just. So if you create a MathTech object, one of the parameters you can pass it is like a string which will be loaded in as the like header file. So if you have it installed on your computer, you can tell Manim to sort of render it after importing some sort of package from your computer. So yeah, like you can do it. I haven't tried it with like commutative diagrams, so I wouldn't like be very surprised if it has some weird bugs, but you can at least try it. Yeah. Okay, what else is there to say? Oh yeah, so remember in the video that I showed you, there was like sort of the ray of light going from the air to the water was sort of broken up into two lines and they were sort of moving along in sync with each other. Let's see how we could do that. So let's A4. So there are multiple ways you could do this. Like you could have two lines and then sort of animate them to move, but you'd have to like tell them both to animate like at the same time, and which you can do, but it's a little finicky. But let's see a better way to do it. So let's say L1 is the line from 2 times left plus 2 times up to the origin. Actually, let's do it to left. And L2 is the line from 2 times left plus, oh no, actually let's do 2 times, oh no, okay, sorry. Left to, okay, we've got 2 lines. I'm just gonna add them. By the way, whenever a lot of the built-in methods like self.add, you can do this. You can add 2 things at once and it'll work fine. So let's do A4 now. Okay, there we've got 2 line segments, but now I want sort of the midpoint to move along, and I want both of them to sort of make sure they're still connected, okay? So what we're gonna do for this is we're gonna use something called a value tracker. So it's another object, but this is an object that is not meant to be displayed on the screen. It is just sort of keeping track of a number for you inside of the animation. And what we can do with a value tracker, or with a lot of other things, but especially useful is when you can do this with a value tracker, is you can add things called updaters to your object. So let's see what that looks like. So L1 is our line, and we're adding an updater to it. And the updaters are in the form of anonymous functions. So if you haven't seen this before, I hope it doesn't look too confusing. But basically, this is I'm writing a little function inside of here, and this function is going to be called on the line whenever, like every frame of the animation, basically. Okay, this is an awkward method name, but it's called put start and end on. I don't know who named that one. It was not me. So, okay, so L1, let's go up a little bit here. L1 is our line from 2 times left plus 2 times up to left. And L2 is a line from left to 2 times right plus 2 times down. The second thing, the left and the left here and the left there are what we're gonna change. So for L1, we want to change the second endpoint, I guess. So we're going to keep it at 2 times left plus 2 times up, and then we're going to move it to x.getValue. So that's taking the value of the value tracker, and we're going to move it, I guess, times right. So -1 times left equals right. Just so you know. Yeah. What else can we do? L2.add. Add updater, and we'll add another updater. And now we're gonna do, we want the one endpoint of one to be the same as the other, so x.getValue. And then it was 2 times right plus 2 times down. And yeah, that's all. Now we've added these updaters to the lines, but we need to actually do something with X to make sure that some animation happens. So what we're gonna do is do self.play x.animate.setValue. So x.setValue would normally just change the value, but if we say x.animate.setValue, it'll change the value sort of smoothly in an animation. And we're gonna change that, I guess, to 3. So it goes in the end to 3 times right. And then maybe we can do another one. Okay. Was it A4? Yeah, I think so. So let's see what it looks like here. Yeah, there we go. So maybe another thing I can tell you about is whenever you have this self.play and you pass it an animation, you can also sort of change a few aspects of the animation. Like you could change the runtime. So if I set runtime equals 3, that'll make it do the same animation, but it'll take 3 seconds, so it'll just slow it down. Let's maybe make this one faster. I don't know why, but I'll make the quality low so it goes real fast. It's just 2 lines. Okay, see, oh yeah, but I should mention that if you set the quality to low, then it only goes at 15 frames per second, which looks kind of bad. So let's try it back to medium. Still pretty fast. There you go. Now the first one takes 3 seconds like I told it to, and the second one takes a half a second. Yes, so I set the initial value to -1 right up here. In x dot, when you created the value tracker, I set it to -1. Yeah. What else? Yeah, so that's a good question. In some cases, you do need to define the things before. So because these updaters are not like making a new object, these are like changing the values that I've already got in some line. But there are also situations where you have a value tracker and you want it to just like change the entire thing, like turn it into a different thing completely. And in those situations, as long as it's sort of the same type of object, so you do still need to initialize it, but you won't have to like always put in all the like data for it. Like you wouldn't have to put in the endpoints if you were changing it to a new thing by using something like you could use, instead of s.put start and end on, you could use s.become, and then you'd pass in some other object. It's a little finicky though, so you should read the documentation if you're trying to do anything like that. Good question. Good question. So actually it's not interpolating linearly. Let's see the animation again, actually. Well, just so you can know that it's not linear. So just watch carefully the first animation. It sort of slows, it's slow and then speeds up and then slows down. It's not a linear interpolation, or it's not a linear in time interpolation. It's like a sort of something like that. But we can change that. We can do this. We can say rate func equals, and this is also weird naming conventions. It's not my fault. Rate functions dot. So, oh no. Yeah. So let's say we wanted to do it linearly. So if we pass it, now I'm like saying the rate func of the play, which is like telling it, what to do, is coming from this other part of Manim called, it's like just a file called rate functions, and it's got a list of a bunch of rate functions you can use. So let's see what it looks like when you put in linear. Yeah. And now, yeah, see, maybe you can tell the difference. Yeah. There's some other ones you could do, like rush into. Oops. Yeah. Again, weird naming convention, but there's like a list of, if you like look at the Manim documentation, there's like a list of a ton of different rate functions. Yeah, so it's slow to begin with and then it speeds up. And that's actually how I did. So there was, in the animation, there was these two broken lines, right? Those are separate objects, but I wanted it to look like it was being created as one object. So instead of just using the standard rate function, I had the first one be drawn with rush into, and then the second one be drawn from rush from. So it's sort of like these two things combined made what is the normal, rate function. Other questions? Okay. Let's see what else we can do. Okay, maybe I'll just show you some of the other built-in things that you can do in Manim. So, for example, maybe some of you guys do graph theory. So you can there is a built-in graph object. So let's see it. Oops. Wait, what did I do? Oh, oops. Okay. So if we want to make a graph, we need to give it a list of nodes and edges. So let's say the nodes are just coming from this, which is in Python, this just means all the numbers 0, 1, 2, 3, and 4. And let's say the edges, I don't know, like 0 to 1, 1 to 2, oops, 0 to 3, 4 to 1. I don't know, should I add any other edges? Let's make it connected. Is it connected? No. Is it? Yeah. Maybe it's boring though. Okay, this should make it look at least like something. And then we can say G equals a graph with that node set and that edge set. And let's see what it looks like. Perfect. Yeah, so you can do graphs, and you don't even need to tell it, where exactly to place each vertex. It sort of does this automatically for you. But you can use some like built-in functions to say place the vertices in a particular pattern. So let's just see a few of those that they've built in. Yeah, so self is just Python's way of referring to the object that this method is a part of. Okay, so A5 is a scene. A scene is another sort of class of objects. A5 is a type of scene, and all scenes have this construct method, but they also have a bunch of other methods that have already been written in Manim. So I need to write the construct method, but I can use the play method, and I don't want any old scene to play it. I want this scene. I want self to play. Okay, does that make sense? Yeah, that's a good point. So this is actually sort of just a notational like thing that people tend to do in Python. So if you have a method, the first argument, like Aranka said, if I wrote apple instead, then I could replace all of these selves with apple if I wanted to. It was self. So self is just like the first parameter for any method of a class. And that is the name of the object that is running the class. Or sorry, that's running the method. Okay. Yeah, so wait just tells the tells it to just render whatever was on the screen, but like for 1 second in a video. You can also like wait for, I don't know, for 2 seconds or 3 seconds. It just says to put a pause in the video, basically. If I didn't write, so here, let me just show you what happens if I don't, and you'll see why I do. So it creates it, but then right after creating it, it just whips it away from you, so you can't see what the result is. So that's why I'm typing wait all the time. Yeah. Yeah, so the default drawing method, I don't think is deterministic. I think there's a bit of randomness in it, but we can see some of the other drawing functions that it's predefined. So I could change the layout. That's a method of G, or I could animate that change layout. And maybe we want it to be the circular layout. And let me just write a bunch of them for you so you can see. I'll wait 2 seconds in between them. And I don't think the default one is random. I think the default one is actually spring, but the spring one uses a bit of randomness. So random is just completely random. Spring is something else that uses a bit of randomness, but also makes it look a little bit nicer. Yeah, it puts them in a random position with springs on the edges, and lets the springs come to equilibrium. So this one's circular. This one's random. And there's the spring one, which looks like it was before. And then there's the spectral embedding. So if you do graph theory stuff, you might have used the library called NetworkX. Maybe you have. And actually, Manim sort of has NetworkX integration as well for the graphs. So maybe I should do import NetworkX as NX. Now, instead of like defining my own nodes and edges here, I'm just going to say like nxg equals nx. And you can use any of the network X like built-in graph functions. So for example, we can do like the Paley graph on 13 vertices. And now instead of just using the regular graph constructor, I'm going to have to use a different one called graph.fromNetwork X. And we're going to pass it that graph, but I'm also going to do something else. I'm going to make it a little bit easier to see. So edge config equals. So this will just make all the edges gray instead of white. So maybe it'll be a little easier to see. Now let's see what that looks like. It's a little slower because it's more vertices, I guess. But yeah, like there's a lot of integration, like I said, with LaTeX, with NetworkX, and since it's just Python, like you can do a bunch of stuff that you could already do in Python, and you can sort of integrate it into your Manim code if you want to. Okay, so there's our Paley graph, and then what is this? There's the circular embedding, which doesn't look as good as I thought it would. Random, spring, and spectral. Yeah. Questions about that? Yeah. I mean, I wouldn't say you can draw anything, but there are quite, no, actually I will say you can draw anything. Anything that is like a grid of pixels, because there's also an image object, which basically you tell it which color every pixel is and it'll draw it that way. But okay, that's pretty slow. If you wanted to do something like a circle, it would be not the best way to do it. Yeah, so why don't I just like show you some stuff. Ignore this for now. So here's the Manim community like homepage. If you go to the documentation, here's the, let me just zoom in for you. If you look on the left here, here's the reference manual, and it tells you basically all of the different, well, let's say all of the different objects. And so if you're interested in a geometry thing, you can have an angle, I guess. So you can draw something like that. An annulus. Not all of them have pictures, I guess this one does. But yeah, they have a lot of different built-in things. And you can also make your own objects. So if something that you want doesn't already exist, you can make it. But they've got a lot of stuff. Yeah. Okay, not all of these are opening up to be as big as I thought they would, and they've got a lot of animations. So they have like the fade in, like I told you, and the create and write and everything. So you can do a lot of stuff with it, I'll say that much. Yeah, actually, let me just show you some of the stuff that you can do that other people have made. Okay, where is it? Yeah, so here's a nice like artistic thing that somebody made that I saw recently. This was made in Manim. And there's also, you can do 3D animations. So for example, someone did something like this. You can do like, artistic things, or you can even have 3-dimensional math things if you really wanted to. And I should mention that there are actually multiple different versions of Manim. So I've been showing you the community edition of Manim, but you've probably seen like this YouTube channel named 3 Blue 1 Brown. This guy is actually the person who like started writing the Manim code before anyone else did. Like he started it and then like made it an open source project, and then people sort of took it off from there. But anyway, he's got his own version of Manim, which is sort of diverged a little bit from the community edition. And in this version of Manim, maybe you've seen, or I don't know if you've seen this video, but he has basically the regular animation stuff, but there's also some interactivity. So you can see he's like moving his mouse and like changing what you see on the screen. So let's see if he does it. Yeah, so he's moving his mouse and you get some sort of interactivity, but this is only with the Manim GL version of Manim. So you can't do this in the community edition, but there's documentation for that as well. You can find it if you're curious. And I guess one last thing, which maybe you've seen, this is not Manim, but it's another animation, and maybe you can guess how to make something like this in Manim. But stop me if you've seen this video. Actually, don't stop me if you've seen this video before, but I think it's kind of funny. So you know the what is it? The Gaussian integral here. Yeah, so I mean that was not made in Manim, but like you could probably do something similar in Manim. It's just to show you that there are other things that you can do with mathematical animation other than do useful things. So I guess that's about all of my time, and that's also about all I had to tell you. So thanks.
Thank you very much, Vilas. For a nice presentation. Do we have questions?
Question.
Yeah, please.
What? Soundtrack for, I don't think this has been implemented in Manim community yet. You can't add like a soundtrack in the, just using the Python code, but it's pretty easy to add sound to a video. You can use a video editor. Yeah. Other questions, yeah. I mean, it sort of depends on how much effort you're willing to put into it. I mean, this thing definitely was more effort to make than like a regular slideshow. But I have given like short presentations before using Manim, and it worked fine. I think it was good. And especially if there is something that is like better explained with an animation, I think it's like pretty useful. Yeah, I mean, Beamer's okay, but I don't know. Yeah, question. Yeah, actually, so this was less of that, but it was more like there was a presentation that me and someone else were both giving, or I guess I did two media as well. So I had a video that I played, and then I wrote on the chalkboard. So you can do that. And yeah, question. Yeah. So let me show you. Let me go back to my video. Yeah, this is Balaton. This is on top of Tihang. Okay, anyway. So in this video, there's a bunch of animations, and I basically cheated. Like I just was pausing and unpausing every time I wanted the animation to stop. But a visual indicator is if you look at this bottom right corner, I've just put a little dot whenever I should pause. So like whenever an animation finished, dot appears and then I pause. So that's what the video actually looks like. It doesn't pause at all, but I do the pausing manually. And I think that works okay for a presentation. But there's actually someone who's been writing a plugin for Manim that will basically allow you to make a presentation that only goes when you click the button and then it plays the next bit and then pauses. But it's kind of buggy and I couldn't get it to work myself. But maybe in the future. Yeah, you could put a video inside of a Beamer, maybe. Is it possible? Okay. Yeah, I don't know. I've never really. Wait, you said there's support for Flash in PDF? Oh. Okay. Well, I wouldn't try that, but that's just me. Oh yeah, you should tell people about that too. I was curious about how this guy has been doing some other presentations using like HTML with embedded HTML presentation, which is just like a slideshow, but with embedded videos. It's an alternative to Beamer.
Other questions? Not then, let's thank the speaker.